I'd like to welcome Professor Ernesto Damiani. He's a professor at the Department of Informatics, University of Milan. He's going to join us online. Is he already on the line? So we're going to hear a lecture from Professor Ernesto Damiani. He's from University of Milan, Department of Informatics. Ernesto, you hear us well?
Yeah, I can hear you.
Okay, so please go ahead.
Wonderful, thank you very much. And I hope you're also seeing I'm sharing my slides, so I hope that you can also see my slides. So I will start. There is the computer science department in Milan, and the work that we've been doing here on this topic and the subject I'm going to speak of is being developed in collaboration with the Institute for Intelligent Systems and specifically the Center for Cyber Physical Systems at Khalifa University in the UAE that you see on the left-hand side of the slide. And we have a flagship project, which is a flagship project on how to weather cyber storms, specifically targeting machine learning and specifically targeting machine learning applied to a number of verticals, which are of interest for the UAE. I don't want to go too much into the details of the application. Let me say just a few words. When you apply machine learning to cybersecurity data, well, you basically tend to follow the classic life cycle of getting samples of a certain label the sample somehow. For example, in malware identification, this is for malware detection type of application. You have malware behavior encoded somehow, and of course in a vectorized form. You have to label the behavior, and then once based on the label, you're going to train a system, and you hope that the system, which has learned from the examples, will also be in production capable of distinguishing malware from a benign software application. So this is, I mean, what I would say that the straightforward type of application of ML techniques, and we have been hearing a lot of promises. So now this artificial intelligence type of approach would sort of improve the capability of some cybersecurity type of applications. Well, there is a problem we know very well because we've been, this problem has been facing it when trying to train antiviruses or trying to train a number of cybersecurity type of application, which is the time you require to update. For example, when a new malware is released and you have to sample the behavior of the new malware to add it to the known samples and then retrain your malware detector. So this is basically a periodic retraining problem. And we are not sure that we can be fast enough and good enough. And also we are not really sure of the level of immunization that you get from, the model which has been trained only on known examples where a new malware has its 0 day and starts spreading in the system, in the network. So basically, there have been a lot of interest in being able to generate behavioral models that basically could apply to a number of malwares, even the malwares which have not been released yet. And in this way to be able to counter the notion of periodic retraining with continuous shaping and plasticity of your machine learning model. So this is something that, again, it's been debated a lot, and we are trying to put this in production as we speak. To bring this type of protection in production, so being able to use a machine learning model to counter threat, you need also to make that model robust. So if you use a model which is going to basically identify malware, what you need to do is also to make sure that the malware is not affecting the model that you are trying to use in order to decapacitate that model from its own capability of detection. And so you need to make the training of that model robust. And robust training is a problem for machine learning models. One technique that you can do is to try to turn a single monolithic model into an ensemble and try to make the ensemble more robust than the original monolithic model used to be. And another technique that you can use is once you have released the model into production, again, this is a model for detecting, for example, hostile behavior on the part of applications, you may want to try to make that model checkable with other models deployed around it in a distributed fashion in order to be able to heal it, just in case someone is interfering with the model plasticity in production. So you see, we have to, when we want to deploy machine learning, we need to make it effective. We need to make it its training timely. We need to make it robust in training, and we will need to make it robust during the inference phase when it is deployed in production. So you see, we have these four concerns that we need to address. And we have, of course, adversaries which are trying to make our four goals elusive. They are trying, and they are basically doing so, at least from the literature. We have the idea that they are doing so by crafting examples that can be used in the training phase or can be used in the phase in production. And those examples are crafted in such a way to either compromise the training or compromise the model once it has been released in production. So there are many techniques announced in the literature about this incredibly, how can I say, intelligent way of crafting examples that will interfere either with the training or with the inference of the model. Crafting also requires intelligence and time on the part of the attacker. The attacker is not just generating noise. It is generating a specific example which will either compromise the training or will interfere with the plasticity, the update of the model in production. And in order to do so, it has also to have an estimate of the internal operation of the model it's going to attack. It is easy to perturbate generating noise, but the generated noise is not really effective in compromising or interfering with the training or the inference of the model. You need to craft it. And the crafting is more a science, an art than a science even today. Definitely, generically speaking, the perturbator, this is the technical name for an example that has been crafted to compromise either training or inference. The perturbators are normal proposed strategies. One of the strategies is to make the perturbator close to the separation surface of the model it's going to attack. You see here the first row that there is a 7 which has been concocted from a tree, and basically this 7 digit this is the MNIST, very well known data set from the literature, and the attacker is supposed to know where the position of respect to the separation surfaces between the class of 3 and the class of 7, and the attacker is concocting a 7 that actually is closer to a 3. So it looks the 7 to a human eye, but it will be misclassified. So this is one strategy, and it works with certain data sets. There are other strategies that require an even deeper knowledge of the model. So you need to know the model you're attacking. You need to know how basically it is mathematically training, how the gradient needed to train it is computed during the training phase. And you will concoct examples that are orthogonal to the gradient. And in that way, you're trying to maximize the impact of your attack on the specific training. So here you see, for example, the image is showing that some examples, the examples that you see there, are orthogonal to the gradient, which is computed during the training of a model. And these examples have been concocted, while the noise examples, which are randomly oriented in the space, they are not maximizing the impact. So you would need a lot of noise to replicate the effect of a single orthogonal perturbator. So the attacker also needs to know the model well and needs to have computational power in order to concoct the example. So you could think, what can we do to defend ourselves? And I don't want to waste your time. Of course, there are many approaches to defend ourselves from this type of attacks. In our project, we use ensemble learning, and we design ensembles that are less sensible to this type of attacks than an original monolithic model, while not being less accurate than this one. So this makes it difficult for the attacker with a limited budget, because he could allocate enough computational power maybe to attack a monolithic model, but attacking the ensemble is going to be harder. This is our hope, at least. And of course, you can do that by creating this robust ensemble by partitioning intelligently the training data in such a way to make harder the work of the attacker. But you also have to keep in mind that you don't want to compromise the accuracy of your own model. Now, before I wanted to go to the end of this talk by asking a provocative question, though. We like all, the community, we all like to work on this type of projects. How can we make our machine learning models used in security robust with respect to attacks of someone who's trying to basically disable these models as they are deployed for protection? Now, is the attacker going to oblige? Is the attacker going to try to generate perturbators and interfere with the training phase? Or is the attacker going to focus on something else? Because of course, attackers, they tended to attack not for the sake of humiliating the researchers that design defenses, they tend to attack to achieve a goal. And so they may go for the point of less resistance. So in order to understand what are the countermeasures and whether we should invest or not on technique for making the training more robust or the inference phase more robust, we need some sort of a methodology to understand if, when, and how the type of countermeasure that I mentioned at the beginning should actually be the ones that I need to apply. And I need to do that not on an abstract definition of the ML model that I want to secure. I need to do this on a concrete instance of the AI pipeline where that model will be incarnated at production at runtime. So this is also our concern in this project. We don't want to concoct the best possible way to make a model robust just for the sake of countering an attack which is in the literature. We wanted to know which is the countermeasure that we should actually deploy in a given scenario, which is a concrete AI pipeline. And in order to do that, we refer to the, you see on the right on this slide, of the life cycle of a machine learning model deployment, where, of course, the training is one side, just one stage. And there are other. So with ENISA, which is the European Agency for Network Security, we worked in a working group in which we decomposed the AI life cycle in fine-grained stages. You see these. And for each of these stages, our idea was to identify the failure modes for this stage and the countermeasures, the threats, and the countermeasures to alleviate those threats. So the given AI pipeline, maybe some of those steps, some of those stages are already secure for some reason independently. For example, the training takes place on a trusted platform, and I don't want to waste my time to create the ensemble that I mentioned before and my resources just to make the model robust with respect to training, because the training stage is not my weak point in that particular incarnation. So basically, we start from the notion of AI pipelines, and which are different from each other, even when they use the same models. So I don't want now to go into the details of this because we don't have time. But our main conviction is that we need the palette of techniques to make the models robust, and we need the methodology to decide if and when those techniques should be deployed in a specific pipeline. And this is an example of a pipeline that you see, which is actually a process built on top of the machine learning life cycle that I showed you before. So from the point of view of the pipeline designer, we are not interested in theoretical countermeasures. We are interested in countermeasures mapped to threats on a specific given pipeline. And so we do basically need a methodology that the security expert can apply. The security expert need to identify the concrete pipeline, to identify the stages of the pipeline that may be subject to attacks, to select and detect the threats associated to the stages, and to deploy the countermeasures. So those countermeasures may be or may not be specifically addressing the robustness in training that I mentioned at the beginning. So this is the steps of the methodology that everybody applies, everybody uses to do threat modeling. And in the case of AI, the notion is that the architecture that we're going to look at is the AI pipeline. And the decomposition is the decomposition of that pipeline into stages. So basically, this is the work we've been doing with ENISA. This is an example of the assets for each stage of the pipeline that we use in order to identify the threats to those assets. And of course, some of those will be the data. And the data threats are the ones, for example, in the injection of perturbators. But you may have other threats that have nothing to do with the specific training phase that we mentioned at the beginning. So here it is an asset to threats map. Basically means that finding for each asset how it could fail to deliver what it is expected to deliver in the AI pipeline stage it is used in. And of course, in these threats, from these threats, we will basically, from these threats you see here, we will basically identify the countermeasures. So this one is a simple pipeline that actually comes from a real examples from a European project, but I don't want now to enter into the details. You see, we have identified the assets in this pipeline. This has to do with the short-term optimization of the production of energy in small plants for energy production in the UK. So here we identify the assets from which could be attacked, and for each asset we identify the failure mode, and from the failure mode we associate a threat, and the threat we generate the countermeasure. Of course, we only handle threats which are known to be referable to a specific asset in a pipeline. We don't deal with unknown unknowns here. And of course, this is a problem, but at least from the compliance point of view, we can make sure that the liability angle is addressed. So, identifying the threats, we are using an adaptation of the methodology proposed originally by Microsoft. It's called STRIDE. We call it STRIDE AI. And if you are interested, there is a GitHub site. You can find examples and all the material for applying this methodology to a generic AI pipeline.
Ernesto, you have 1 more minute. Sorry, just
Okay, but I'm there. Okay, so the methodology, of course, does not only identify the threats, it decomposes them, and for each of the atomic element in a threat will identify the basically the corresponding countermeasure, which may or may not be the countermeasure for making the training robust that I explored at the beginning. Okay, so this is all. Our technique is being tried out on a number of concrete pipelines in a number of verticals of interest, and we are specifically targeting energy, transportation, and healthcare. These are the 3 types of verticals that our project is targeting. And of course, I hope that some of those who listen to this this morning are interested to take a closer look at the methodology, to take a closer look at our compiler, and we will be, of course, open to interchange and discussion with everyone. Thank you very much for listening this morning.
Professor Ernesto, quick question. Given all the threats that you mentioned, do you still think it's worthwhile integrating AI into the pipeline?
Yeah, So some of the threats that were mentioned basically are threats which are specific to attacks to the machine learning models in training and in inference. There are other threats. For example, sensor spoofing during inference is a threat which is documented in the field. So some of those threats are not documented in the wild as we speak. Others, which are maybe less attractive for the researchers, are. So this is why we want to try to do both. We want to try to address those type of threats that we, for the moment, are only addressable in the lab, but are fancy. But we also wanted to provide a concrete way to address those threats which are not documented in the lab too much, but are actually have been found in the wild, like sensor spoofing during the ML inference, which is well documented in a number of verticals.